All right, let's talk about trigonometry. And look, I know what you might be thinking. Flashbacks to math class, right? But forget all that. We're going to uncover what it truly is, an incredibly elegant, really powerful way of thinking that helps us measure, well, pretty much the entire universe. So let's just dive right in.
I mean, really think about it for a second. How do you find the distance to a star that you can't possibly visit, or figure out the height of a massive mountain without actually climbing it with a tape measure? The answer to all these seemingly impossible questions, it lies in the rules of trigonometry. It's really the language of measurement.
So, where do we even begin a journey this big? Well, we start with something we all know, something familiar and pretty simple, the right-angle triangle. So here it is, the main character of our story for now. Everything in basic trigonometry is built right on this shape. The key thing to get here is that the sides have these special names, but, and this is important, only in relation to a specific angle, an angle we're just going to call theta. Okay, let's get the lingo down. The side directly across from our angle theta, that's the opposite. The side right next to it, the one helping to form the angle, that's the adjacent. And that long slanted side that's always opposite the 90-degree angle, that is always the hypotenuse. Pretty simple, right? Get these three down and you are ready for the magic. And here is the absolute core idea. For any given angle in a right triangle, the ratio of its sides is always the same. We give these ratios names, sine, cosine, and tangent. And how do we remember them? Well, with probably the most famous mnemonic in all of math, so, ka, toa. Sine is opposite over hypotenuse. Cosine is adjacent over hypotenuse. And tangent is opposite over adjacent. This is your beginner's toolkit, the whole shebang right here. So now with Soka Toa in our back pocket, we're feeling pretty good, right? Like we can solve all kinds of problems. But then we hit a wall, and it is a big one. Our simple, reliable little rulebook has a fatal flaw. See, here's the problem. Our entire system, opposite, adjacent, hypotenuse, it only really makes sense inside of a right-angled triangle. And in a right triangle, the other two angles have to be sharp. You know, they have to be what are called acute angles, less than 90 degrees. But the real world isn't always so neat and tidy, is it? What happens when you turn more than a quarter circle? I mean, what does opposite or adjacent even mean for an angle of 300 degrees? Our simple toolkit it completely breaks down. We need an upgrade, a serious one. And that's where the hero of our story comes in, the unit circle. This is the professional upgrade that takes trigonometry from being just a simple tool for triangles into this universal language for rotation, for waves, and for cycles of all kinds. So what's the big deal? Well, by placing a circle with a radius of exactly 1 on a graph, we can suddenly track any angle you can possibly imagine. 120 degrees? Just rotate counterclockwise. Negative 30 degrees? Okay, rotate clockwise. Every possible angle now has a unique point, a specific address, right on this circle. Okay, now here is where it all clicks. This is the big reveal. If we just draw a right triangle inside our new unit circle, our old rules map perfectly onto this new system. The length of that opposite side, that's just the y-coordinate of the point on the circle. And the adjacent side, that's just the x-coordinate. It's the exact same idea, just expressed in a way more powerful system. And this gives us a serious upgrade. Because the hypotenuse is now the radius, which is always 1, the math gets so much cleaner. Sine of any angle you can think of is just its y value on the circle. And cosine, it's just the x value. That's it. It works for every single angle, forever. A truly universal definition. Now that we have this universal system, it's not just about a new definition. We've just unlocked this entire toolbox full of powerful new formulas and what are called identities that let us solve unbelievably complex problems pretty easily. So let's take a quick peek at these power tools. You've got the Pythagorean identity, which comes straight out of the unit circle. You've got the law of sines and cosines, which, get this, let us solve any triangle, not just right-angled ones anymore. Then you have things like double angle and sum and difference formulas that let you manipulate angles in really complex equations. This is the professional gear. Okay, so we can find the ratio if we know the angle. But what if we want to go backwards? What if we have the ratio? Let's say we know sine is 0.5, and we need to find the angle. Well, this is where we need inverse functions. But they come with a tricky little problem. And this quote from our source material really nails the issue. A sine value of 0.5, well, that could be 30 degrees, but it could also be 150 degrees or 390 degrees. I mean, you can just keep going around the circle forever. If your calculator gave you all of those answers at once, it would be totally useless. So what do we do?
The solution is actually really simple and kinda elegant. Basically, mathematicians all just agreed on a rule. Let's restrict the range. So for the inverse sine function, for example, it's programmed to only give back an angle that's between -90 and +90 degrees. That way, you get one single predictable answer every single time. Problem solved. All right, so we have come a long way, right? From simple little triangles to circles to these powerful identities and inverse functions. But so what? Why does any of this actually matter out here in the real world? Let's bring it back. I mean, it's because of trigonometry that we can survey land and design buildings. We can create maps and navigate ships across the entire globe. We can calculate the orbits of planets in astronomy. And maybe most importantly, because of that beautiful wave-like pattern we see in sine and cosine, we can describe and work with everything from sound waves to light waves. Seriously, it is everywhere. And this is a perfect example. A complicated-looking problem like this, it seems impossible at first glance, trying to calculate all these distances and heights. But with the tools we've just talked about, the law of sines, the law of cosines, this turns into a totally straightforward calculation. That is the power you now understand. So here's the real takeaway. Trigonometry might have started with triangles, but it ended up revealing this deep, fundamental pattern about how the world works, the rhythm of cycles. You see it in the tides, the seasons, you hear it in the sound of a musical note. It's even in the alternating current in our walls. So my question to you is, now that you know what to look for, where else do you see the rhythm of sine waves?